Welcome to NE204 Lab 8. In this lab, we'll consider a geometric analysis of the Fitzhugh-Nagumo model, which we'll abbreviate FHN for short. What we'll look at in this lab is numerical simulations of this model, as well as an inspection of the phase space. And we'll try to use both of these techniques to build our intuition about the model dynamics. One goal in particular will be to understand how the dynamics change and how our geometric analysis changes as we adjust parameters in this model. As in all labs, text preceded by a percentage sign will indicate a comment. I'll use these comments to provide notes for you and maybe ask questions and explain some of the answers. Remember, comments are also always critical and useful in your own code to make sense of what you've done if you come back to it or if you want to share your code with someone else. Always comment your code. It's a good habit. So let's begin with an inspection of the equation for the Fitzhugh-Nagumo model. Now in class, you wrote down the equations for the FHN model. Let's look at those again for reference. So here they are. Here are the differential equations for the Fitzhugh-Nagumo model. A question, how many variables are there in this model? We find in this case that there are two variables in this system. We have the variable V, which we might think of as representing the voltage, and W, which we might think of as representing a current in this system. So we have two variables in this system, V and W. Now, how many parameters are there in this model? Again, let's look at the equations. What are the parameters? Well, we have the parameter I, which we can think of as representing an injected current, and then we have the parameters A, B, and tau. So there are four parameters in this model system. One of our goals today, and in this lab and in your homework, will be to understand how the dynamics change as we adjust some of these parameters. So notice the Fitzhugh-Nagumo model is a second-order system. It consists of two variables, V and W, that change in time. We have a dV dt and a dW dt. The Hodgkin-Huxley model, remember, was a four-dimensional system. We had four variables to worry about. While the LIF model, the leaky integrate and fire, was a one-dimensional system where we also had to include a hack. Let's begin by computing numerical solutions to the model dynamics. To do so, we can write our own code to simulate the Fitzhugh-Nagumo model. To begin, let's compute some numerical solutions to the model dynamics. To do so, we can write our own code to simulate the Fitzhugh-Nagumo model, which we'll see is similar to the strategies we've used to simulate other types of models, like the leaky integrate and fire and the Hodgkin-Huxley model. So from Blackboard, please download this function, fhn.m, and let's discuss this function to get a sense for how it behaves. And again, we'll see that the same simulation strategy we applied to other models also works for this model. So let's take a look at this function. I've downloaded the function fhn, Fitzhugh-Nagumo.m, and here it is. So here's our function. Notice the first line of this function, we define the function name, which matches the file name, fhn, and we define a series of inputs. In this case, there are 6 inputs, and I'll get into what those mean. So we have these 6 inputs, and the function returns 3 outputs, which we can probably guess are the output variable v, the output variable w, and then a time axis, which is useful for plotting. Okay, so what are these inputs? Let's look at those. Well, fortunately, the person who wrote this code did a very good job of defining the inputs. We'll see if this good commenting holds throughout the rest of the code, but at least this initial definition of these 6 inputs is very clear. We need to specify a starting value for our variable v, that's v start. We need to specify a starting value or initial value for our variable w, that's defined by the variable w start. We then specify our 4 parameters, I, the input drive, 2 recovery parameters, a and b, and then the time constant for the recovery, tau. Okay, and what is this function output? The variables are defined in a intuitive way. V represents the membrane potential or voltage, so that's returned. The second output represents the recovery variable, W, and then T represents a time, or I guess it should be a T-axis in this case, represents a time axis, which is useful for plotting. Good. So that's looking at the inputs and outputs to our function. Let's now see how this function behaves. We can start looking at the nuts and bolts. So what do we need to do? Well, first we define a time step. We set it equal to 0.1 in this case. We then are going to have 2 output variables, v and w, and we initialize them. So let's set the value at the first index 1 equal to v start, and the value at the first index of w, also the index 1, equal to w start. So we set the initial conditions for these 2 variables, v and w. And then we're going to run a for loop here. This for loop is going to iterate over 5,000 steps, and we're going to implement or iterate over this variable t. And what do? Well, we're going to take the current value of t, and then we're going to update it using our function. So we should be able to see our function here. And if we look closely, we see that we have v of t minus 1/3 v cubed minus w plus I. So that's the differential equation for our variable v. And this first line is telling us how v changes in time. So given the current value, we're going to update it by using dt times our function f, evaluated using the variables at the current time, and that'll define v at the next time step. And we use that same procedure to update w. So we want to know what is the value of w in the future at time t plus 1. We take the current value and then add to it dt times our function, in this case, the right-hand side of our equation for dw dt. So these equations, what should we notice here? Well, first, this procedure is similar to the procedures we used for the leaky, integrate, and fire in Hodgkin-Huxley. Given what we know now, update it to get the value at the next time step, t plus 1. We should also be able to see the differential equations for the Fitzhugh-Nagumo model. And we should see these in the terms that dt multiplies. So we should see the right-hand side of the differential equation for v and the right-hand side of the differential equation for w here. So we'll run this iteration, stepping forward in time in these small steps. dt is 0.1. We're going to do that 5,000 times. And then we'll save the output v and w. And we'll also return this time axis, t-axis. Good, so that's our function. Again, the most important thing is to be able to see the Fitzhugh-Nagumo equations in this function. And here they are in lines 23 and 24. Okay, so let's return now to our part 1 of the lab 8. And what we'll do is let's simulate this model numerically. To do that, we're going to need to specify the 6 inputs for this function. Here they are. We'll set the initial drive to the system to 0. We'll set our recovery variables to have particular values. And we'll choose starting values for v and w equal to -1. Okay, so with this, I'll execute these now. So let's execute these 6 variables. I see they appear in my workspace. They all have a single value. They're scalars. And now let's call our function. We'll call the function Fitzhugh-Nagumo with these 6 inputs and save the 3 outputs. So I'll do that here. So I'll paste that function into my MATLAB command line, and I'll evaluate it here. It evaluates very quickly. I didn't get any errors, so hopefully this worked okay. Okay, and again, notice that the function fhn, it takes 6 inputs. We've specified numerical values for all of those inputs. And also notice that this function returns the 3 outputs, v, w, and t, as we see here. And these outputs are defined as defined in the function itself, the fhn function. So with these outputs, let's now have a look, and let's see what these outputs look like. And to do that, let's plot one of our output variables, v versus t. So we'll make that plot here, and we'll label the axes in a descriptive way. So our horizontal axis, the x-axis is time, and our vertical axis is the variable v. So let's see what the solution looks like. So here's a plot of v on the vertical axis and t, time, on the horizontal axis. So how would you describe the long-term dynamics of this system? We see that after an initial transient, we have this large increase and decrease. But after this initial transient, after about the first 50 milliseconds of this simulation, what happens? Well, the dynamics settle down and not much changes. Right? The system eventually comes to rest at a value it looks like near maybe -1.2 or -1.3. So to answer this question, how would you describe these voltage dynamics? There's an initial rapid transient. There's this rapid change in voltage. Where did the dynamics eventually go? Well, they stop changing, right? They eventually come to rest near this constant value of -1.2 or -1.3. Something important and fundamental to remember about our Fitzhugh-Nagumo system is that it is a 2-dimensional model. So to fully understand the dynamics, we need to visualize both the first variable v and the second variable w as well. To do that, let's plot both variables in the same figure as functions of time. To do that, we'll use the subplot command in MATLAB. So let's do that here. Let's make a subplot. It'll have 2 rows and 1 column. In the first entry, we'll plot t, v, and we'll label the axes, the horizontal axis time and the vertical axis voltage. Then in the second subplot, we'll plot t and w. So the second variable is a function of time, and we'll label the axes with time on the horizontal axis and w on the vertical axis. So let's do that. I'll execute this command now. And we get the following figure. In the top row, we're plotting V, the voltage, as a function of time, where we have this initial transient, followed by the voltage settling down to a constant value near minus 1.2 or 1.3. And if we look at the variable W, we see again we have an initial rapid transient. W rapidly increases and then decreases and settles down to a value near minus 0.6. So in this case, we're visualizing the dynamics of our full system, the variables V and W, as functions of time. And if we think about the question posed to us here, how would you describe the combined dynamics of the two-dimensional system? Well, one way to describe it is that there's an initial transient, rapid changes in both V and W, and then the system settles down. We see that V approaches a constant value and W approaches a constant value. Now, this is just one way of visualizing the two-dimensional system. Here we're plotting both variables as a function of time. We'll look at other ways to visualize this two-dimensional system and see if that provides any more insight. In part 2 of the lab, we'll perform a geometric analysis of the Fitzhugh-Nagumo model. In class, we discussed a 5-step procedure for this geometric analysis, which we'll implement now. Let's try to implement this 5-step procedure for our FHN model. Step 1, we'd like to draw the two-dimensional phase space. Remember, this is a two-dimensional model. We have two variables, V and W, that we'd like to deal with. In the previous part of the lab, we looked at each of these variables evolving in time. What we'd like to do now is draw these variables as they evolve simultaneously in a two-dimensional phase space. You can think of this two-dimensional phase space as a plane. For example, your computer screen that you're looking at now. So let's try to draw this. We'll look at the dynamics of this system as V and W evolve in the two-dimensional plane. In class, you wrote down equations for the two nullclines of this system. Remember, to solve for the V nullcline, we look at the differential equation for V, dv dt, and we set that dv dt equal to 0. We now have an algebraic equation that we can solve. Let's isolate W, and what we find is this new expression, which we've written here in the lab. W is equal to something in terms of V. We have V minus 1/3 V cubed, and then plus our parameter I. What we'd like to do now is plot this nullcline. To do so, we're going to evaluate the expression above for W using a range of different V values. So to do that, let's first define our vector V. We'll do that here. We're going to choose V to extend over some range. We're going to go from minus 2.2 to plus 2.2 in steps of 0.1. So let's make a vector that has these V values. So I evaluate that expression here. Now, to evaluate the V nullcline, we need to define one more thing. We need to specify our parameter I. To start, let's set I equal to 0. So I'll define that here. We'll set our parameter I equal to 0. And we're now ready to define the V nullcline. To do that, let's write down a new variable. We're going to evaluate W for the V nullcline. We're going to set that equal to our values of V minus 1/3 of values of V cubed plus our parameter I. And notice we've specified numerical values for everything on the right-hand side of this equation. V values is a vector. It goes from minus 2.2 to plus 2.2, and I is a parameter, which we've set here to 0. So if we evaluate this expression, good, I don't get any errors. So a question, why are we using dot hat 3? Why are we using this notation? Why not just a hat 3? Why is that dot important? Something to think about. Remember, we'd like to perform this operation on each element of our vector. So with this V nullcline evaluated at different values of V, let's plot it and let's see what it looks like. So what we're going to plot here is our V values, which go from minus 2.2 to plus 2.2 in steps of 0.01, versus our W for the V nullcline. So let's plot that. We'll use a dashed line and we'll label our axes. We have V on the horizontal axis and W on the vertical axis. So we'll do that here. And this is what we find for the V nullcline. We have W on the vertical axis, V on the horizontal axis. And if we look at this nullcline, we see it has a particular shape. It starts at high values, it goes low for a bit, it has a relative minima, a relative maxima, and then it goes low again. So it has this cubic type shape. Okay, Let's now plot the W nullcline for our Fitzhugh-Nagumo system. To do so, we're going to need to define a new variable. We'd like an expression for the W nullcline. We'd like that expression to have W equals stuff. Once we find that expression, we'd like to plot this W nullcline in terms of our V values, so the same variables we've already used. And in order to do this, we need to define what is stuff. So how do we find this W nullcline? When we do so, we'd like to use our same range of V values that makes it nicer to plot, and also our same parameter values, A, B, and tau as we've specified above. And then we'd like to plot this W nullcline on the same figure as our V nullcline. So how do we do this? We need to define our W nullcline. Well, let's go back to our differential equation. We have dW dt is equal to a bunch of things on the right-hand side. In order to find the nullcline for W, we set dW dt equal to 0. We're then left with an algebraic equation. There are no more derivatives in this equation. And we need to solve this equation. And here we're going to solve this equation for W. So we'll take W, move it over to the left-hand side of this equation. We then divide by B. And what we're left with is a new expression. And what you'll find, what you showed in class, is W is equal to V minus A over B. So let's go back to our code. We now have an expression for the W nullcline where we have W is equal to stuff. And that W for the W nullcline, we've said, is equal to V, where here we're going to use our V values. So the values of V that we've already specified in the vector, they go from minus 2.2 to plus 2.2 in steps of 0.01. So we have these V values minus A, our parameter, divided by B. So here we have a new expression for our W nullcline. We solved for it analytically in lecture, and perhaps you've also done it again here by hand. And now we have this new expression. We're going to evaluate it. So let's evaluate this W nullcline. I'll do that here. And then let's plot it. So we're going to plot this W nullcline versus our V values on the same figure that we've already used to plot our B nullcline. And what you should find in this case is a new figure. We had our V nullcline here in blue. It's a cubic function. It goes down, up, down. And then we have our W nullcline, which is a line. And that's shown here in red as a red dashed line. Why is it a line? Does that make sense? Well, if you look at our expression, we have W is equal to something in terms of V. There are no squares or cubes or anything. So this looks like a line, right? We have V on our horizontal axis is like our X value. W is like our Y value. So we have this linear relationship for the W nullcline. And there we have it. We've plotted our two nullclines for this system. That finishes our step 2 in our 5-step procedure of displaying, doing our graphical analysis for the Fitzhugh-Nagumo system. Step 3 of our graphical analysis, let's locate the fixed points of our Fitzhugh-Nagumo system. So we defined the phase space, our two-dimensional plane in step 1. We then drew the nullclines for the V and W variables in step 2. And with that, we're now ready to locate the fixed points of our Fitzhugh-Nagumo model. So, with the parameter settings that we used above, how many fixed points are there in the Fitzhugh-Nagumo model? And where are they? To answer this question, it's useful to look at our phase plane with the nullclines plotted. Let's do that now. So here is our phase plane. We have our V nullcline in blue, our W nullcline in red. Now remember, on the V nullcline, dV dt is equal to 0. That's how we define the V nullcline. While in red, dW dt is equal to 0. That's how we define the W nullcline. So if we want to find the fixed point of this system, we need to find the points where both dV dt is 0 and dW dt is 0. Where does that occur? Well, in this case, it only occurs at one point in the plane, at the intersection of our two nullclines. So what's happening at this intersection? Well, we know dV dt is 0 because we're on the V nullcline, and we know dW dt is 0 because we're on the W nullcline. And if we're at the intersection of these two nullclines, then both dV dt is 0 and dW dt is 0. So that defines a fixed point. In this case, our phase plane and our nullclines give us a simple visual way to identify the fixed points in this system. We just look for the locations where our two nullclines intersect. At these intersections, both dV dt is 0 and dW dt is 0. If both derivatives are 0, that means V is not changing and w is not changing. dv dt is 0, v is not changing. dw dt is 0, w is not changing. So the full two-dimensional system is fixed. Neither variable is changing. The location of this intersection of the two nullclines defines a fixed point in our system of the Fitzhugh-Nagumo model, and we can see it directly in our VW plane. Now on to steps 4 and 5 of our graphical analysis of the Fitzhugh-Nagumo model. What we'd like to do in these steps is look at the flow, how the dynamics change in the neighborhood of each fixed point, and also other places in the phase plane. So in part 3, we located a single fixed point in the VW plane. We know that if we start the model dynamics at this fixed point, then we stay at the fixed point. That's why it's called a fixed point. The dynamics here are fixed. V and W are no longer changing if we start at that specific fixed point. But what happens if we start near the fixed point or somewhere else in the two-dimensional phase space? To answer this question, we'll look at the vector field for this model, and that's the goal of this section of the lab. To start, let's define a range of values for V and W in our two-dimensional plane. I'll choose a particular range here. You might investigate how your analysis of results change if you adjust these ranges. So for the V values, we'll go from minus 2.2 to 2.2 in steps of 0.25. And for the W values, we'll go from minus 1.5 to 1.5 in steps of 0.25. So I'll define those two variables. We'll then use one more function to visualize the vector field for this system. Please go to Blackboard and download this function, FHN, Fitzhugh-Nagumo _ vector _ field. Let's briefly look at this function and see how it behaves. Here is the function. We see it takes 6 inputs. It takes our two variables, v and w, which we specify as vectors over some range, and then it takes the 4 parameters for this model, I, A, B, and tau. So what's happening inside of this function? Well, we define a range of v values we're going to investigate. We define our two nullclines, which we looked at in the previous sections of this lab. We're then going to plot the nullclines, the v nullcline and w nullcline, and on top of this, we're going to place our vector field. So to do that, we call this function mesh grid. We evaluate essentially the right-hand sides of our differential equations. So what is the change in v and change in w? And then we're going to use another function in MATLAB called quiver, which makes little arrows that correspond to our vector field. We then label the axes and set the axis range. So there are a couple of functions here that you might investigate in more detail if you're interested. For example, what does mesh grid do? And what does quiver do? You can look at those functions in MATLAB help if you'd like to investigate this further. But for now, let's just apply this function and see how the vector field behaves. So we'll go back to our section of the lab. And let's apply this function. Again, this function takes 6 inputs. We need our v values and w values, as well as all the parameters we're going to use in this model. And there are other built-in functions. You can look at those if you want. But let's apply this function now and try to understand the output. So we'll evaluate this function. I'll do that now. And let's examine the plot that results. So here's the figure returned by this function, FHN _ vector _ field. Let's look at the axis. We have W on the vertical axis and V on the horizontal axis. And we can see our two nullclines. We have our V nullcline in blue, it has the cubic shape, and our W nullcline in red. It's a line. These are very similar to what we had seen before, and we can find our fixed point in this two-dimensional plane. It's the intersection of our two nullclines. So what's been added to this figure? Well, now notice there are a bunch of little arrows in this figure, and these arrows correspond to the vector field. So what do these arrows represent? Well, they tell us if we choose a particular point in this plane, how does that point evolve in time, in the next instant? So for example, if I'll place my cursor here in the bottom right, if we were to start at this location, which is a particular value of WV in this plane, at the next moment in time, we expect to move over to the right and up a little bit. Right, if we were to choose another point, maybe in the top left quadrant, we see if we were to choose a point here at a negative value of V and positive value of W, in this upper left-hand quadrant, we see that the next instant in time we expect to move to the left and a little bit down. And what happens if we move closer to the fixed point? We see that these vectors get smaller and smaller, which tells us that the change is getting smaller and smaller. And what we would expect to find exactly at the fixed point is no change in V and W. Remember, it's a fixed point. If we start there, we no longer move. And perhaps With your mind's eye, you can begin to trace out how the dynamics might evolve in this two-dimensional plane. So let's try to do that. If we start in this bottom left quadrant, where my cursor is located, we move a little bit to the left at the next moment in time. And what happens? Well, we keep moving to the left. Right? We look at the vector field. These arrows are continuing to tell us to move to the left, maybe up a little bit, to the left and up a little bit, to the left and up a little bit, to the left and up a little bit, until we hit this blue null-cline. What do we know about the blue null-cline? Well, here dv dt is 0. If dv dt is 0, we're no longer moving side to side, so we're not moving along the horizontal axis. So when we're at the blue null-cline, we can only be moving up and down. And if we look at the vector field, it tells us we should move up, right? Those little arrows are tending to point up. So if we take our cursor, we're now moving up. We cross the v null-cline, the blue curve. We continue to move up in this plane by looking at the arrows, and now these arrows are telling us to move up and to the left, up and to the left, up and to the left. So we're circling back now in the plane, we're moving up and to the left. I'm looking at the arrows, they're telling us to keep moving left, keep moving left, keep moving left, until we hit the W null-cline, which is shown here in red. What happens at the W null-cline? Well, we know dw dt is 0, and remember W is our vertical axis. So if dw dt is 0, W is no longer changing. We're not moving up and down when we're at this W null-cline. We can only move side to side, left and right. And we see in this case, we continue moving left. The arrows are telling us, keep moving left, and eventually we start moving left and down. So by inspecting this plane and looking at the arrows, we can get a sense and try to trace out by hand how the dynamics may evolve in this plane. And in the next section of lab, we'll plot a trajectory on top of this plane and see how it behaves. As a last step in our visualization of this system, let's look at a trajectory and see how it moves through our phase plane. So in the previous steps, we plotted the two-dimensional phase plane, we indicated the null-clines, we found the fixed point, the intersection of the two null-clines, and drew the vector field. Let's now include in this figure an actual trajectory that the model follows. We tried to sketch this out by hand, but now let's simulate one numerically and put it on top of our figure. To do so, we're going to again simulate the model like we did in part 1, and let's do that here. Let's repeat that analysis. So the first thing we'll do is define all 4 parameters in our model. We'll set I equal to 0, A equal to minus 0.7, B equal to 0.8, and tau equal to 12.5. That specifies the 4 model parameters. We'll choose 2 initial conditions, an initial condition for our V variable and an initial condition for our W variable, and then we'll call our function FHN, Fitzhugh-Nagumo. We'll specify the 6 inputs, the starting values for V and W, and then our 4 parameters. And let's evaluate this function and save the outputs, the output variable V, the output variable W, and then a time axis, which sometimes can be useful. So let's evaluate this, setting our parameters and our initial states, and calling the function. I don't get any errors, so that's a good start. So now, by doing this, we simulate a trajectory from the model. Earlier, we had plotted these trajectories versus time. So we plotted V versus T and W versus T. But now, instead, let's plot V versus W directly in the two-dimensional plane. And then to do that, we're going to call this function plot. We're now, instead of using T, we're going to plot V comma W. So we'll do that, and we'll also specify a range for V. Let's go from minus 2.2 to 2.2, and for W, minus 1.5 to 1.5. So let's evaluate that plot and look at it. It's also useful, I know I didn't include it in the code, let's label the axes so we don't forget which axis is which. So we'll specify an X label, let's make that a V, and our Y label, let's make that W. So what do we see in this two-dimensional plane? Well, again, on the vertical axis, we're plotting W. On the horizontal axis, we're plotting V. How does this trajectory evolve in the two-dimensional plane? Well, we start at the point minus 1, minus 1. I'll put my cursor there. So we start at this point minus 1, 1, minus 1, minus 1, and then what happens? Well, we see that V rapidly increases, so it's moving to the right while W is slowly increasing. Then W rapidly increases. V slowly starts to decrease. And then we spin back down and W rapidly decreases, V slowly increases until we hit this endpoint. So what's happening at this endpoint? Why is it going to this particular point in the plane? If we were to run the simulation for longer, would that point keep going? Would it keep moving around? Would it keep going somewhere else? Or why is it sticking there? Why is it ending up at that particular point? Right? That's a good question. And we'll see, we'll try to make more sense of this when we plot also in this figure the vector field and the null-clines. So again, what we're plotting here is a single trajectory. We can think of this as v and w evolving in time. They start at one point and they form this partial loop, eventually ending up at this other point in the two-dimensional plane. One other way to see this is we could select this tool on the top of our figure, our data cursor. I'll select this data cursor and then I'm going to click right at the beginning of our curve. And what it should specify is a black box, so you can see that black box here, and then the values of x and y. And we can I'll hit right arrow on my keyboard, and we can watch this selected point move in the two-dimensional plane. So we can think of this as the trajectory that's evolving in the two-dimensional plane. And what happens? Well, we move up and to the right, and then we move slowly up, or quickly up, and then quickly to the left. So again, watching this trajectory evolve in the plane, I'm just holding down the right arrow key. And then what happens? We start to decrease. The trajectory is now zooming down and to the right. And again, I'm just holding down the right arrow key on my keyboard, and we're watching this trajectory. What's happening? Well, it seems to be getting slower and slower and slower and slower, evolving more and more in time. It's kind of slowing down. And what it looks like is that it's coming to rest at this point. Right? It's coming to an equilibrium. Right? Very interesting. So what is that point in the two-dimensional plane? Let's continue to investigate. So in order to do that, let's return to our code. We're going to plot on top of this figure the vector field. So we'll call our new function fhn underscore vector underscore field. We use this to plot the vector field and the null-clines. So let's do that here. So we'll evaluate that function. Let's put our let's freeze the graphics and then put on top of this figure our trajectory v versus w. So we're going to plot that again. And then let's evaluate this new figure. So here's this figure. On the vertical axis, we have w. On the horizontal axis, we have v. We can see our two null-clines. We have the v null-cline in blue and the w null-cline in red. We also have our vector field, all the little arrows, which tell us the instantaneous velocity, how things move at particular points in the plane. And then we have our trajectory that we simulated. And that trajectory is shown here as the black curve. Remember, it starts at the point -1, and then it cycles around the plane, eventually coming to rest somewhere. So one question we had from our previous figure, where does this trajectory end up? Well, we see this, the trajectory in this case ends at the fixed point. And maybe that's not so surprising. We might expect in some types of models that the dynamics, no matter where they start, end up at a fixed point. We've seen that at least in our analysis of one-dimensional systems, and here we're finding it, in this case, for a two-dimensional system. Now, let's also look at this plane and try to track the trajectory as it moves in the two-dimensional space. Now, we had done this in a previous figure, but in that figure, we didn't have the null-clines and we didn't have the vector field. So let's try to do it again here. Again, I'm going to select this cursor tool, which is helpful for us to move along this black curve, and I'm going to select our black curve. So we begin at this point, -1, -1. If we look at the arrows in the vector field, they're telling us to move right and up. And if we move along, as we move along this black curve, that's exactly what's happening. We're moving right and up, right and up. And again, this is consistent with the vector field. It's telling each point to move right and up, right and up. And what happens, eventually we reach our v null-cline. What happens at the v null-cline? Well, at this point, we know that dv dt is 0. So we're no longer moving side to side. We can only move up and down. Our arrows tell us we move up in this case. And we see that as we pass through the blue curve, the trajectory moves almost straight up. After we pass through the v null-cline, the arrows are now telling us to move up. And depending on where we look, it could tell us to move right and up or left and up. But essentially, we're moving up. As we keep moving up above the blue null-cline, we see that these arrows are telling us to move mostly to the left and a little bit up. And we see that our trajectory continues to move, in this case, to the left and up. We eventually reach the w null-cline. What do we know about the w null-cline? Well, here, dw dt is 0. If dw dt is 0, we can't move up and down. We can only move side to side. And what we see in this case, as we pass through the w null-cline, we move left. There's no up and down movement. We're only moving left. We can see that by looking at the arrows in our vector field. So passing through the w null-cline, we continue to move left and a little bit down. We then pass through the v null-cline again, in this case, moving downward. The trajectory then moves down. We see the arrows in our vector field are pointing down. and to the, if we look to the left, they're pointing down and to the right. If we look to the right, they're pointing down and to the left. And so we continue moving down, in this case, very close to the V null line, near that blue curve. And what happens, we get closer and closer and closer, eventually getting very close to that fixed point. So what we find in this case, following a particular trajectory, we start below and to the right of the fixed point. We start in this point -1, -1. We move through the phase plane and eventually end up at the fixed point. And we move through this phase plane in a particular way that's determined by the vector fields, these little arrows that are shown here, which are determined by the differential equations we use to solve this system. Now, in the assignment associated with Lab 8, you'll be asked to further investigate the Fitzhugh-Nagumo model and examine how these pictures change as you adjust parameters in this system.